Alright, but here we go. Let's talk about the actual section. So the section that we're in section 10.5. Okay, what we're talking about in this particular section was called tangents. Okay. There's a couple vocab words I want to talk about today. Number one, let's discuss what a tangent is real quick, because I know it's been since last week since we talked about that. We talked about the point of tangency, all that. So there's a couple different things. The big thing I want to talk about with tangents is this concept that I hinted at on Friday, but we never really ventured into. It's called a common tangent. Okay, I basically just did a few drawings on the board, and we didn't really come back to it. I said Monday is going to be the day where we really discuss a couple different words with it. There's a couple different forms. That's what I'm going to discuss today. Once we're through that, then we'll get into some examples where we actually try to do a couple examples of how to use your theorems that we talked about on Friday. So I believe the videos and stuff are online from Friday, so you can watch them. I made sure it was on the website. I don't know if I changed the main page, but in the actual drop downs, all the videos should be there. So made sure this morning they were there. But this is kind of our goal today. It doesn't seem like a lot, but I want to do more examples today of what the homework will eventually look like. We only have, I think, 2 sections left this week. 2. It's this section and the next one. The next one uses this concept of tangents a lot, and the other word that we're going to discuss today, because I'm going to intro a new vocab word today, so a new vocabulary. Okay. Because this is going to help us with the tie-in for later sections. And I always like to introduce it with this stuff, just because you can kind of see the comparison. But the new vocab word today that we're going to discuss is called a secant line. It's called a secant. We'll discuss that. So, all right, let's jump in. Let's talk about these. Let's talk about what a tangent is. Okay, so here's a circle. Here's my center. Okay, what do you remember from Friday? What is a tangent to a circle, please?
Line that touches a circle once.
Touch the circle once, okay? And it's a line, right? So it goes on forever, continues in both directions without limit. That's the definition of a line. So this would be a good example of a tangent line. Now that one spot where it hit, it's a perfect touch, and it doesn't go into the circle itself. So that's a tangent line. Again, how they name it, because I know the homework will ask you name the tangent, blah blah blah. So call it line L. You can call it different letters. Maybe we call this A and B, or this is pronounced line AB and put little arrows above it. Their lines continues. That's a tangent line. Now, what we discussed on Friday was the actual location where it touches. This spot right here, it has a specific name. Anyone remember what the name is called? Where it touches. Haley, what do you get?
Point of tangency?
Yeah, it's the point of tangency. The actual location where it touches the circle. Point of tangency. Now that was kind of apparent in one of the theorems that we talked about. That it was the first one, theorem 1010, that a tangent line has a very specific property with that point of tangency, that when you actually draw the radius in here, so the radius going from point C here, that's the center, going out, so when you actually draw the radius of that circle from the center to the outside, it should make a perfect 90-degree angle there. That was the theorem 1010 that we talked about on Friday, because it said of something of the form that if you're in the plane of a circle, a line tangent to the circle or a line is tangent to a circle if and only if it is perpendicular to the radius at the point of tangency. So this is the only reason why this is a tangent, is because it's perpendicular to the radius at that point. If it wasn't a 90-degree angle there, that would not be a perfect tangent line. It would actually become one of these other words that we'll discuss today, which is called a secant. We talked about the proof on Friday. We did. It was called a indirect proof. It's when you start with the assumption that the theorem that they wrote was wrong, which I know is weird. We assume they're wrong, and we try to show why they're wrong, and then eventually, at some point during the middle of that proof, we figure out that my assumption that the theorem was wrong, my assumption was incorrect. So we had to go back and kind of fix it, and so it forced it to be a 90-degree angle at that point of tangency. Now that's what our examples will use today. That whole concept of a 90-degree angle is perfect for the type of math we've actually learned in here. So that's what we're going to look at. So we'll come back to this picture here in a minute. We'll do a couple of examples of it. But that's called the point of tangent and a tangent line. Now, the other word that we discussed was called the common tangent. Use this concept, but what a common tangent is when you have, multiple circles. I think I drew two examples, two pictures on Friday, but you can do multiple. You can do a bunch of different circles. And what we have here is we have lines that connect the two circles. Okay? And these could be lines that could go on forever, blah, 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 blah. Okay, now, these are called common tangents. It's a line that is tangent to both circles, okay? Or multiple circles if you have like 3 or 4 of them. But the thing is, we never really discussed that there's different types of tangents. That one of the examples we had was called an external tangent. This is an external tangent. An external tangent line. Now, the reason why, the definition of an external tangent, it is a tangent to both circles that does not cross the segment connecting the centers of your circles. So here's the center of both circles. Let's call this M and N. The actual tangent, the segment itself, does not cross the segment that connects the centers. That's what the book says is an external tangent. The tangent line does not intersect the segment connecting the centers of your circle. So it's on the outside. Now the other way, like how could you draw a line that would actually cross that dashed line? That was that second example I drew on Friday that we had. Okay, we had both my circles, same picture again. But you draw a line like this, where it touches both. Okay, that line, which is tangent to both circles, it hits the circles once perfectly, that is called an internal tangent. And I tried to show examples, or I shouldn't say show, but talk through examples of what would use that type of system. Okay, and what we talked about on Friday was like belt system. We use pulley systems, but the belt system of a car uses that, certain belts and whatnot. Question?
But they're both common tangents.
Yeah, they're both considered common tangents. They're common to both circles. It's a tangent that both circles share, but they're just different types of common tangents. We have an external versus internal. And the definition, obviously, of an internal is a tangent to both circles that intersects the segment connecting the centers of your circles. So that tangent does cross the segment connecting the centers. That's how you know if it's internal or external. Okay, but again, yes, you are correct. Maybe I should put that above. These are still considered common tangents. Kind of easy concepts. All right. Now we have a couple more examples I want to talk about, but the examples we talked about in class on Friday was like the external tangent idea would be like a bicycle chain, that idea. A pulley system can have that where you have multiple gears and stuff. I think the example I used in some other classes was like at Bill's Family Foods, you know how they have that little like conveyor belt where you put your groceries? There's a couple of rolling pins underneath those, in theory. Target has them, but there's a couple rolling pins, and that the actual like rubber mat that goes over top of it is actually tangent to all of them. It like touches perfectly in all of them. So, but again, so it's the actual chain on the bike or the mat. But now internal tangent would be like a cable or pulley system or a belt system wrapping around multiple gears, that type of thing, a rope. That's actually how you alleviate pressure on a very heavy object to pick it up. You use multiple different tangents and internal tangents, and you have different pulleys. And the more you add, the less weight it will be on the actual pull itself. So there's a way to to alleviate pressure on an object by putting in certain size pulleys and gears in there and putting them in certain arrangements. So kind of a cool concept. All right, now that was called common tangents. Now the other thing that we didn't discuss, and this is something I said I wanted to go through on Monday here, but it was that circles themselves can actually be tangent to each other. And I think I did like one picture of this on Friday. That you can actually have circles that are physically touching each other, like that. Okay, that concept is like a gears of like a clock kind of a thing, or gears in an actual machine that the actual teeth are touching. Okay, now here's the weird thing. This is going to seem very weird. You could still draw a line that goes right through the middle of them, right? That line is still a tangent line to both circles. Okay. Now here's the weird thing. The actual line that's going right through the middle. So I think the example I used on Friday was like paper feeding through a printer. You have the gears, the wheels of the printer itself feed the paper in, and the paper goes right through the middle of them, and it kind of directs the paper where it needs to go to be printed. That line is actually considered to be an external tangent, or what I should say, the circles, I should say, are considered to be externally tangent to each other. That's a better way to put it. So the circles themselves are externally tangent. Externally tangent. The circles are, I should say, not the line. The line in the middle is considered an internal tangent. Okay? Because it would be this. That if you connected the two circles with a line, the line actually intersects that internal tangent. So, but the circles themselves are externally tangent, even though the line itself is internal. Now, there's the other situation, and this is one I don't know if I drew on Friday. This is one I'm worried about. Is that you could have a system like this. That. Okay? And this situation is where you have a circle inside of another circle, but they perfectly touch at one point. Okay? That is where circles are called internally tangent. The circles are considered to be internally tangent. They're connected on the inside of each other, right? One circle inside of another. The goofy part about the circles being internally tangent is that the line that connects them, the line that touches them, doesn't cross that midline. It doesn't cross the line, the segment that connects the centers of the circle. So the line, if I were to actually draw a tangent line here, that would actually be considered external tangent line, because it doesn't cross the line that connects the centers. Here's my centers. You can see my tangent line wouldn't touch it. Now, the best example I can use for this, like if you had like a pocket watch, you could like flip it over, and usually a lot of pocket watches you can see the gears and linkages on the inside of the actual clock itself. I'll try to bring it in my example. I have a pocket watch where you can see all of it. But the actual idea that the best example I've ever seen of this is like planetary systems. They can, what NASA does is they tend to, we're going around the sun, but we have the moon itself kind of rotate around us. But this is what NASA uses. This is how they use slingshot effects. That you can go around like the moon, and then slingshot off it using its momentum to carry you further into space. So you do a quick internal and do a quick external. So I think one of the examples that NASA did, like this is weird. This is almost like 15 years ago, when NASA landed the Mars rovers on Mars. They did this weird slingshot effect where they left Earth. So here's Earth, and here's the orbit that we're making with the sun. Okay, here's the sun. Right? The sun's not a perfect center; it's kind of off center. You'll learn that in pre-calc. But okay, they're going around. They went, and we have that orbit around us, which is the moon. This is the moon. This is Earth. This is Mars. And what they did is they left at a certain point where they let the probe fly. It rotated around the moon and then slingshotted out into space, where it eventually intercepted, as Mars came around the corner, it intercepted Mars perfectly, and then it caught on the gravitational point of Mars, so Mars passed it. So they had two opportunities to do this, where they could go in front of Mars. So if Mars is here, they could go in front of Mars and then rotate backwards through it, because the gravity would pull it back in backwards, so it would really slow it down. Or they could go past Mars, let Mars pass in front, and then go past it and then rotate in around it and then eventually land, which I believe they used the second attempt. It was the one that used like the least amount of energy. It was more natural to come in instead of going backwards and wrapping backwards around it. It didn't cause as many stress on the actual probe itself. And then the cool part was once Mars gravity captured it, all they had to do was just let the gravity pull it in, and then once it was through the atmosphere, they blew up a balloon around it, basically like a huge balloon that surrounded the actual probe itself, so that when it hit the surface, it literally bounced on the surface like a big bouncy ball. And then when it came to a rest, when all the sensors on the probe itself noticed that it wasn't moving anymore, then it deflated and it let the probe go. And it was on Mars for what, the last 15 years? I think one of them got stuck, and the other one, I believe the internal batteries died because it got covered in Martian sand, basically, and it couldn't collect solar power, which is unfortunate. But yeah, they collected data, and the mission itself was only supposed to last like 3 months, and it lasted like 12 years because they figured out some systems so they could use solar power. They fixed things on the fly as they went. It was really kind of a cool project. But it was using this concept, like internal tanks where they do slingshot effects to speed them up so they could go out into space further. And that's kind of the concept of how they got a probe onto the Titan, the moon of Saturn, Titan. I think the next couple of probes that they want to send out into space were, they did one to Jupiter, which they recently crashed into Jupiter to just see the density of the atmosphere. I think their next probe docket is to send one out to the nearest solar system, or the nearest solar system where it has planetary bodies, which I think was supposed to be scheduled this year, or maybe next year. And that one's a long term, that's like 20 years, something like that. And then to land one on the ice moon of, I think it's not Europa, what is it, Io? Of Jupiter, where it's covered in ice. And I believe there's water in it. So, but kind of cool projects they have coming out, but this is the idea, like they use this concept, which is just like a very elementary, geometry-based problem, but they do it in such a way that it makes sense. They have to use minimum fuel to actually go out into space, which I think is kind of cool. But kind of cool projects. All right, now getting back into focus where we're in geometry now. We're talking about tangents, right? The actual tangent line itself, using that theorem 1010, was that tangent lines are perpendicular to the radius, right? This is the perfect concept. So one of the problems that we're eventually going to see is that we can actually find lengths of pieces. So like for instance, maybe I wanted to figure out this length from here to here. So C out to this point L, like what is that distance? And we knew the distance from A to L is, let's say this is 8, and we knew this is 6. And we can find this X right here. Because maybe you knew the radius of your circle, you knew how far if you were to fly past it, but we want to figure out this intersection point. Okay, up there. So this is a right triangle. So these are the legs of your right triangle, because why I know those are the legs, they touch the 90-degree angle. Bless you. This is the hypotenuse of your right triangle. Because it's the one wall that doesn't touch 90. And so doing the Pythagorean Theorem, you do the legs squared, add those together, so 6 squared plus 8 squared. That's a squared plus b squared equals the hypotenuse squared, which is c squared. That's, I know, one of the homework problems that they ask you. So this is what, 36, this is 64. You add those together, you get 100. And how do I get rid of the power of 2?
Over.
Yeah, and what do? We don't divide by it, but square root, yeah. Square root of 100, which is 10. Because remember, you're trying to think about what number multiplies on itself to give you 100. Well, it'll be 10 times 10. All right, questions, comments about the actual problem? Okay, let's do another example, because there's one example in the book that they threw in there, and I was kind of just looking over kind of the problems that we're going to be eventually getting, and the problem they had was subtly more difficult than most people would think. And it's kind of this clever little problem, and it was this. Okay, so here's my circle, here's my center. A, let's call this B, let's call this D down the road, okay, something like that. And let's say this is 5, this is 24, okay? And the question isn't to find C to D, like this one. You know, the length from C to, what was that point, way down the road, whatever that point was, okay? But the question was, on this particular problem, was find this piece right here, which is B to D. A very clever type of problem. It's actually a two-part question. It's actually really, really clever. Okay? And I believe they say, like, go to 2 decimal places. Okay, fair enough. All right, so to find BD, what you have to find is do this problem over again. So you do the whole Pythagorean Theorem to figure out, you know, C to D, the whole hypotenuse idea. Because if that is a true tangent line, which they always say in the directions, you have a perfect 90-degree angle, so you do have a right triangle, so you can do the Pythagorean Theorem. So what you want to find is all of CD. And once you have CD, then it's easy to find BD, the piece of it, which we'll talk about here in a minute. So, and that's the part we want to get. But again, let's figure out this whole length right here. We'll call this X, okay, C to D. So, Pythagorean Theorem. Can somebody set the Pythagorean Theorem for me?
24 squared plus 5 squared equals X.
Okay. 5 squared plus 24 squared equals X squared. Okay, again, the two legs squared, these are the legs, they touch the 90. So 24 squared, 5 squared, add those together, that makes your X squared. Good. So this is 25. This number 24 squared, something like that. I don't know, is that right?
Yeah.
Okay. 576 squared. And then you add 25 to it, which is 1, carry a 1 over, that's 9, so 0, 601. And then you take the square root of it, which they said it was going to go to decimals, which now I understand why. So you're trying to figure out a number that multiplies on itself that gives you 600. Okay? It's big, right? It's got to be bigger than 24. It's the hypotenuse. It's got to be bigger than 24 on that picture. So let's see. 25 times 25 is 625. So it's got to be smaller than 25, probably bigger than 24. 24 point something?
24.51.
Okay. 24.51. All right, we'll go 2 decimals. That's good. And again, how you do this, you can just type that in your calculator. Square root key is usually right around the number 7. Somewhere you have to usually hit second. Yeah, there's some calculators you don't. But you type that in, 24.51. Okay. That makes sense. It was going to be the biggest rule. Now, the question though, is how do you find this little piece? Ha, say it.
Subtract 5.
Subtract 5. Here's the reason why. This is very clever. The 5 is the radius, right? You can move the radius wherever you want. It's like a hand on the clock. So this 5 can technically rotate to here, so this is 5. Really, really clever. That was actually really good that you saw that. So the 5 can rotate up, and now you can take the whole 24 and subtract 5, and that gives you the other piece. Actually, I'm impressed by that. That's really good. So, what is that, 19.51 if you subtract 5 off that? 19.51, that's correct, I think it is. Okay, questions, comments about the problem? Hopefully I did it right. Okay, we good so far? Okay. I got one more with this picture, and then we're going to go to the second picture, and then we'll be done today. Because I only have 2 more left. 2 more examples. That's all I want to cover. Okay? Alright. So the next one here, and this one is kind of a more tricky based problem, but, and it's got some new math in it that I'm hoping that you have seen in Algebra 1. I'm hoping. So that's why I want to cover it today, to see kind of where you guys are at in your Algebra 1 skills. What you remember. It's been a while, over a year now. But, okay, there's this problem in your eventual notes, something like this, let's call this N. It had something like this, here, and it had this, okay? This is 12, this is 6, and let's call this N to P, and let's call this point Q down here, and that is a perfect right angle. And it wanted to know the length of MQ. That's the question. MQ. This problem's a little more difficult than you think, but once you see like the math behind it, hopefully it'll make sense to you. Like it'll click a little bit, but it's significantly more difficult than the last one. Right? There's a little more work to be had. All right. Now, before we start, what can you tell me about MQ and MN? They have to be the same. The radius, right? The radii. So whatever this is, let's call this x. That stick has to be the length of that one, MN. They have to be the same, right? Because it's not like the last problem. You can kind of swing this radius wherever you want. It's hand on the clock. It doesn't really change size depending where you move it. That will help you out with this problem so that we can actually solve for x. All right. All right, so what we'll do here, x squared plus the 12 squared. Okay, those are my two legs. So it's the Pythagorean Theorem again, x squared plus 12 squared. Now, the big wall. What is the big wall, though? What are the pieces?
X plus 6 squared?
Yeah, you have to go x plus 6, and you have to square that thing, the whole thing. X, whatever x is plus 6, and you have to square it. That's the hypotenuse, the big side. That's the part I want to see if some people have ever seen that before. That's the part I want to know, like, your thoughts. Like, how do you attempt to do that part? Because this part I really can't do anything with, other than making that 12 squared 144. No, you don't distribute. You don't put the 2 through. What does the power 2 actually mean? Yeah, you multiply the parentheses times itself. So that's what power 2 means. You don't distribute. It means this, that you actually have 2 of them being multiplied together. Now this is the part that, I don't know if we've really covered a lot of this in this class. We really haven't. But now number one, I'm hoping that you have. What is the math that you have to do there? What is it called? Say it again?
Distribution.
It's distribution or FOIL. That's the 2 words. Distribution is the correct word that I use. But yeah, you have to like multiply them together. And so distributing, like how I think of this is my method of doing it, is that you take the first item and you take it times everything in the back. So you're distributing, right? And once you're done with that, you'll have a couple answers, right? You'll have the 2 answers. Then you're going to take the 6 times everything in the back. So you do like one at a time, but it is distribution. What this is actually called, it's called FOIL. F-O-I-L. First, outer, inner, last. That's the way that they say it in Algebra 1, right? The first terms, the outer terms, the inner terms, the last terms in both parentheses. So, but for me, it's basically just 2 distributions. That's just how I think of it. So don't like overthink it. If there's more items back there, fine. You just take the x times everything, write it down. Take the 6 times everything, write it down. That's how you do it. So this is going to be x squared plus 144. All right, now doing the math here, x times x, x squared. X times 6, 6x. Okay, so there's the 2 parts I had marked in blue there. Now the last 2, I'll put these in red here. 6 times x, 6x, and 6 times 6, 36. Okay, there you go. So that's kind of doing first, outer, and last. That's doing everything. Back, change that just so maybe this will be a little bit better to look at, color coding wise. Make sense how I did it? Now, why I'm choosing to do it this way? If you start moving things around, things cancel out. That's the beauty of doing this. That's why I thought this problem was clever in the way they had it set up. Because the x squares are gone if you bring this over and you like subtract it across, or if you write it across an equal sign, it either adds or subtracts, they cancel out. It's 1 minus 1. So those are gone. But then what I'm left with is this. I have the 12x's over there and the 36. And now that's just a simple algebra 1 problem. So you'd have to subtract the, okay. Last example is if we had an exterior point to a circle. This is the last theorem that we had on Friday. It was theorem, what was it, 1011, that's the theorem we had. So we have a circle, and you draw exterior points, let's call this A, call another one B, call another one C, and this is the middle point, right? If you were to draw tangent lines to a circle, what we talked about on Friday is that these sticks have to be the same length. And they have to be the same length, okay? No matter where it's from. So those two would be equal. If I draw the other ones from A, that could be a completely different dot, but these two sticks are equal to each other, those two personally. And then if I went from another point, B, going this way, those two are equal to each other, okay? Not all 6 of them are. Just from the one point, like if you're going from point B, then these two are. Okay, that was theorem 1010. It said in a plane of a circle, a point exterior to the circle contains 2 tangents to the circle, and the tangents are congruent, they're equal. Now, why this is important is what we're going to talk about on I guess Tuesday. That'd be tomorrow. We'll do a couple examples of this where they're going to have you draw like, or they have a big picture and they have a bunch of external tangents coming from these exterior points, you know, and they're going to have you try to find the perimeter of the object that's left. So maybe it's a triangle. You can kind of see the triangle. If I put these like straight across from each other, you could have a big triangle, so you could add up the walls. Okay, if it was a big triangle. So we'll talk about that more tomorrow. I'll do a better drawing, but this is the one property I want to remind you of. That was your theorem 1011. Questions, comments about the theorems though that we talked about? Okay. The goal today was to really focus on those, the whole Pythagorean Theorem idea. So there's a couple more examples of that. Tomorrow I'll do a ton more of these. These are my focus tomorrow. We'll probably see maybe a small assignment. When I'm talking small, like nowhere near the last one. Like small assignment on this stuff because there's not too many grounds to cover. And then I'll get to it. One word we didn't even talk about today. We'll talk about secant. Well, I'll just throw it in tomorrow. I'll talk about it. One of the words I want to intro because it's not until the next section, but it kind of ties in nicely with this. Okay. All right. That's it for today. You're done. Make sure you're getting page 727 done. All that good stuff.